Stated record. Yeah, thanks. Always miss
Sir,
this.
hello.
Yeah.
Hmm. Sir, I just have a small thing to check. If it is okay, I can go ahead.
Yeah.
So on the previous lecture, there was a slide on, slide number 45, which is
Mm-hmm.
on TF-IDF, right? And
Mm-hmm.
just a trivial thing. So the number of terms in the document is showing as 9, right? And
Mm-hmm.
if you can maybe go to that example, it's on slide 45.
Now you
But the
tell me, I remember. Yeah.
term seems to be 8 only, like machine learning is a subset of machine learning, right? That was a document. And the terms there are only 8 terms are there, but it shows that the number of terms as 9 in the document.
Mm, mistake, yeah. Let me check. Mm, you have to check the class, right? Yeah. 40, a
45.
lot of files, right? The number of what you said, the number of
The number of terms, mod D, that is written as 9, right?
correct.
But- So how it is 9? There are only 8 terms.
You can consider some words as two, right? So, for example, I'm not sure. Ideally, TF-IDF should consider exactly 1, 2, 3, 4, 5, 6, 7, 8. Yeah, you can consider 8. That is
Okay,
not a
and
problem. You consider one more word in that. That will be better than. So calculation doesn't change.
okay, okay.
Yeah.
And the other thing, sir, on the similar slide, the term
Mm-hmm.
learnings, right? The learnings,
Mm-hmm.
you know, the number of terms for learning says 3, but it's only 2, right?
Correct. Yeah, you're right. So who is this? You have
This
studied
is
nicely.
Prabodh. Yeah, Prabodh Saxena. I was just
Very good.
trying to
Yeah,
revise, sir. Yeah. Thank you.
good. Good. So I will not correct the slide. It's okay. Good that you found out. It's good. Let others also find it out, right? They should know it's correct or wrong. Right? It's not a big mistake. There were a lot of
Sure, sir.
mistakes when I was studying MTech.
Sure, sir. I was just
Okay.
trying to confirm if I'm missing
Yeah.
anything
Right.
on. Yeah,
Right. See, your concept is right means you would have found out the answer, right? So that calculations are ideally to say it's all you have to blame the LLMs for that. I use a lot of LLMs to get that generated. Don't have much time to check each of the numbers. Mostly calculations I would have never checked because I am preparing slides for every lecture nowadays. Not nowadays for this semester. Earlier semester I would have gone through like this semester. It maybe the calculation somewhere mistakes might happen. But if you understand the concept, that's fine. I think you will get that. Good. Okay. I cannot change the number because that's all. Yeah, I can change, but okay, let's see. I'll not change as for this one. If there is any other major mistake, then I'll try to change. Okay.
sure, sir.
So
Sounds
since you
like
have
that.
already
Yeah.
mentioned, yeah, and since I already mentioned here in the recording, people will listen and then understand, right? Yeah. Anyway,
Makes sense.
thanks. Anybody
Yeah.
else, if they found it also, let me know. Okay. So it's good for others also, right? Who will come back, will learn it in a very fast mode during their exams, right? So, okay, good. But otherwise, the concepts are clear, right? So, does anybody have any issues with the concept which we discussed? How that is calculated and why that is having two limitations, right? There are two limitations on that, right? So, and then why we had to go for BM25. That's the main point you to learn as a AI engineer. calculations are fine, right? You don't, nobody is asking you to do calculations in your company, right? That is, but for, yeah, in exams, you people will ask, yeah, don't worry about marks, right? You're all working people. MTech degree is fine. Around 75 plus should be a good takeaway from this course. But the concepts why you have to have BM25, first of all, why you should go for a sparse models beyond the dense models what we discussed last class. And in dense model, sorry, in sparse model, why not TF-IDF? That's a very simple method, right? So there are two limitations. So what are those two limitations? And then why we have to go for BM25? Whether that solves both the things? Actually, not two limitations. It has four limitations. In general, if you consider sparse models, it has four limitations. In that, two are solved by BM25 and two more are solved by dense, because sparse was the earlier one which came, right? So ideally, we should have started with sparse and then come back to dense as its limitation, but we went other way around because we started with transformers, which will lead to encoder models, which are the embedding models. So we maintained that flow and then we uh, used.
So just one more thing, since you're instructor in charge there. So the formula for BM25 seems to be very lengthy. So we have to, remember this formula for the exam for any numericals, or will it be provided as a part of question?
No, 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 I am with you. Not
Okay.
required.
Okay, sir.
Arey, I am
Thank you.
like you guys only. Just that you consider me as a senior. I will not surely ask for this uh, formulas and all.
Sure.
Right? Yeah, that is not necessary also. So nowadays everything ChatGPT gives. Only you should know what to search for and how you have to search for. Right? That's very important. So how you have to search is also fine, but what you have to search, because what happens is basically even I use a lot of ChatGPT, not ChatGPT. I use Cloud, ChatGPT as well as Gemini, like cross-platform verification of three LLMs beyond my knowledge. So what happens is like you put the requirement on one chatbot, you get an output, then you copy paste this to another one, re-verify it, copy paste that to another one, re-verify it, and then at the last three times after three chatbots response, I'll still find there are a lot of mistakes. That's where if you couldn't find, which means you are lacking in that subject. That's what I can guarantee, because even I used to, whichever subject I do not know, like for example, sometimes medical, I used to check, like medicines. I want to check what is the chemical composition, whether it's good, it has side effects. Sometimes I check, even though we should trust doctor only, but will I check for sometimes? I do not know anything about it, right? So I have to believe. I don't even go to the next chatbot because the first chatbot, what it gave itself is too much for me, right? So if you can, but for some topics which I am good at it, like you are also good at it, you will never get satisfied even after five chatbots. So that is the, when you are able to get to that level, which means you are good in that subject. That's what I can say in a very fair level of logic, you can say like that. So try to get to that level. That is what is required from this course also, because all of this you may not you may get it from chatbot. In fact, I have developed it using the chatbot itself, but point is it's not just completely purely from a chatbot. No chatbot can ever give you this syllabus for sure. It's my experience has gone into this slides and the course design. That is what it makes it little special. You will never find it in anywhere in the world. I'm not boasting. Of course, it's completely customized for me, right? So my thought process, what I should do based on what I have taught last 4 semesters and how, what they like how students grasped it, and I'm working in the same field. So what the data scientist or the MLOps guys require, right? Data engineers require to know to deliver some AI application. I'll not say 100% accurate. Nobody has reached 100% accurate. If somebody says that's just an influencer, like बोलते हैं ना, LinkedIn influencers, don't believe on that. You can get to 70 to 80 uh, for a more confident output. So that's why even if you go to chat, any chatbot, Gemini or Chat GPT, they'll give you I think Gemini has a sentence like, please double check. Gemini can make mistakes. Please double check the answers. So that's where that it lacks that 10 to 20 percentage of the accuracy. So it also point is that it also searches internet, right? So internet data is also not validated, right? It searches everywhere. Even though you take textbooks, you can find a lot of textbooks. So including my own the slides. If you think my slides are Bible, then you are like this is like from God's book. This is also wrong, right? So you have to put in your brain to understand what is wrong here, what is not wrong here. When you study and go beyond a level, then you will be able to identify. So same way chatbots also. So A applications, when you are delivering, you can give a guarantee of 70 to 80% accuracy, or whatever is the metric you wanted to call, answer correctness or groundedness, whatever it is, right? So that's what we can deliver even though you do everything. So most of the other work, even today's study, this part, if you see this part, cost engineering is mostly for latency purpose, right? Latency as well as cost. Yeah, I agree for cost, but latency is also a very major point to be considered as a factor to be reduced using these logics. Okay. So, and these are all the general model landscape we'll see. Okay, that's very interesting, some of them. So this is very not so much mature. It is okay, good models, but nobody uses this. Not many uses this, not nobody. Okay. And but here currently chatbots, if you build with a simple RAG application, I think around 40 to 50% you can reach based on what is how good is your data, right? So as the famous, I don't know who's the person, I think Alfred or somebody, he mentioned uh, the output depends, it is exactly proportional to the data quality, right? So we do pre-processing, but how much you will do pre-processing? You can do for 10 documents, 20 documents. When it's like in our chatbot, what we developed earlier, it was around 50,000, no, it's not 50, 60,000 documents. 60,000 documents. What kind of generalization concept you can give for the pre-processing? And all are unstructured. That's the most complicated stuff, right? See, if it is structured like anything, you have the same format like invoices, right? Invoices, 60,000 names. You give millions and millions, I can process it if the invoice is from a particular vendor, right? So, for example, I'll tell you one travel. So, in my previous organization, there is one use case. The travel department came in. They asked, "Okay, we have lot of hotel receipts. Okay, the hotel bills, right? The employees go and stay in different locations, different hotels, and then produce the bills as a reimbursement, right?" So when they produce the bills, all are scanned. Okay, this is the first point. Second point is each hotel bill's format is different. So now complexity starts, right? So first simplest complexity is the scanned. So it is OCR. Second one is it is all different formats. Like somewhere hotel name will be written in the top, somewhere hotel name will be bottom, somewhere it will be mentioned as accommodation amount, somewhere it will be written as room rent amount, right? Somewhere it will be written as room rent plus uh, like something he would have taken breakfast or some. juice or water bottle he would have taken. So both the bills they would have added, and they would have given both these separately, and then finally in that same row they would have added. So you have to identify all these differences. Another third complexity is that this language, like because the previous organization, like so many countries, so every country have their own language, right? So hotel receipts are in their own languages. So again, there are a lot of differences there. And another thing is the currency rate. So the currency rate for that particular hotel on that particular day when the bill was there, that should be taken from the internet. So on that day, what is the currency value equivalent to the dollar? Then I have to convert it to the dollar, right? So you have to with your API to your this currency converter and date it to that day, right? That's the point. So like this, lot of complications are there, and what they wanted was just a simple thing. The requirement is that you finally get the room rent, and then there would have been the travel people always bargain with the hotels and freeze a amount, right? So for an employee, it is 5,000 rupees. Room is 3,000 rupees. They are going to give. Okay, so this is the bargain amount. But sometimes the hotels charge the employees 3,500. So there are a lot of people in the company also. Like, I think around 15,000 people, more than 15,000, I guess. So lot of bills. Everybody travels. So lot of receipts come in. So manually checking everything was little difficult. Lot of contract people we have to hire and then get it checked and then ensure that okay, the hotels are charging based on their earlier bargain rate only. Not they are not overcharging something. So another difficulty is that uh, it's very quite interesting. Another difficulty is some hotels day one they will charge less, day two they would have charged more. So but at the end of 3 days, they would have charged exactly equivalent to the bargained amount. So, and every day's bill will be in one page. So you cannot just compare one set with the exact value. So a lot of difficulties in this. That's what I was talking about. Like complexity, in the data is very, very important to handle. Almost 50% of time goes in that complexity itself. So remaining 50 percentage, all these what models to be chosen, what to be done, and based on. So sometimes you always feel, array, put everything to GPT or a bigger LLM and then get it done. But the cost is very high. Your management will not agree. They'll say it's instead I will use manual people, humans to do the work, right? So that's a complication. But you have done a great work there. So a lot of SLMs we have used in between. Okay, so coming back to today's lecture. So one more thing I want to tell. So suppose if you guys also have some good use cases like this, complicated use cases, first jot down all the complications. Like simple objective looks very easy, right? So once you hear the first sentence, like the travel type, right? So you just have to take one hotel bill, compare that with the bargain rate of the travel department, and then say whether it is higher or lower. Yes, that was the easy one. But then when the complexity increases, uh, the like your importance as a AI engineer increases, right? So more complexity you handle, your name will fly high. So that's a good thing. So that's interesting also. That's what we are paid for, right? So we have to do it, not just complexity increases. I heard earlier times people just keep blaming. Arey, ye aise, aise. That is why you are paid for. You have to handle the complexity. If it was very easy, the travel department would have created the AI application. Correct. It's a point to be noted. I don't know. Many people just keep blaming and telling that, oh, this is it is not required like this. Travel department has to do something and then give it to us. So travel department will do the data processing. And why AI engineers are there here to solve that using AI in some cases. Like I'll not say every complexity can be cured by AI, but as per my experience, almost 80 to 90 percentage can be cured. Cured means resolved by using some good models or good workflows. That's what you should learn here and then apply it. Simply saying that, oh, so like one example is like database. Database, like there are 3,000 tables in a database. And there are some foreign connections. You understand, right? The foreign relationships are missing in this schema. In this schema, no, XML files. Okay, not XML files. You can say the table scripts and XML files also. It is missing. How will you find it? That's a very interesting problem. So, what was these prior? Like even the architect, he gave this answer. I though stopped it, but the architect gave this answer that, oh, this has to be manually entered by the team, the other team, right? The application team who hosts the database. This is the easiest answer to say that I don't want to work and I am paid freely. Instead, he mentioned this answer. I was wondering why are we here then? We should not be paid at all, right? So think there is simplicity and we have to think and then resolve it. But if people are saying that, okay, it is the other team's work, I don't say 100% of it can be solved. 90% you solve, remaining 10% you tell uh, they do to manually. If you tell all the 100% to be done by manually, it will take 6 months. So 6 months you are paid extra. So you should get laid off for 6 months and then join the company back after 6 months when they will complete the manual work. Okay, sorry to be rough here. So if you're managers, right? So we expect some good results. So in fact, I am not a pure manager. I'm not a very good manager also. I'm more of a tech guy. So managers are very professionals. I am zero professional. So I'm a pure tech guy, talk direct in face. If I can't do, even I am not fit here. As simple as that. Okay. Okay. Sorry for the extra gyan. Okay. Coming to today's class, we'll go through fast. So these are all some of the tables which you can go through, right? So these three things are the major things what we currently look after in job also. Dense transformers, I think you understand what is dense here. So it is basically uh, the self-attention and the typical self-attention plus the feed-forward network transformers. Okay, so transformers mostly currently in these cases currently most of them are only decoder only transformers. Very rarely because it has to generate the next word, right? We don't use the encoder part because decoders has the encoder into it. So if you understood our explanations earlier or the previous your ML paper also, not ML paper, DL paper, you'd understood that. Mixture of experts is little bit different. We'll see that little later. It's very easy to understand. Nothing great in that. Just that one gatekeeper is there to route it to the correct self-attention. Okay. Not self-attention, the feed forward block where the non-linearity actually happens. Third one is the small LLM. Smaller LLMs, for now, you consider 1 to 3 billion parameters are smaller LLMs. Okay. Small language models. Okay. Like 5.3, Gamma, Queen. There are some encoders also. Similarly, smaller encoders are also have come in. So you can consider these for specialized tasks and edge devices. Like in mobile phone, if you want, I guess many of our mobile phones which we have applications, right? They will have one smaller LLM in your app itself. So very quick queries like hi, hello, how are you? All these will be answered by this small LLM, the small SLM. It's what SLM, right? So it'll answer. So only if the query requires really it has to be routed to a bigger one, then we use the when then it sends to the original, like for example gamma you take. So gamma, I think uh, 1 billion model is also there. So for example, in your consider that in your mobile that 1 million model is already there, 1 billion model or whatever this, or 250 million model. It's already there. So for smaller queries, it will answer. So if you ask a very complicated query, okay, tell me what happened in India yesterday. So for these queries, it has to route it to the API, the original Gamma 2.5 Pro, right? Or the complete workflow. It doesn't go to that particular LLM. Actually, it goes to the workflow. In that workflow, one part is Gemini 2.5 Pro. You understood, right? So anything if you didn't understand, let me know. Okay. And otherwise, specialized task, what we mean is you can fine tune it for a specialized task. So it's not like specialized task. It is not specialized information. Understand that fine tuning does not guarantee you to learn your knowledge base. So it is like, for example, okay, you are a generalist, right? So, for example, if you want me to learn, like I'm like a SLM, okay. If you want me to learn medical, like terms in the medical, I will not learn. SLMs cannot learn new language, new terms. SLM can structure the way out it can do. So it is specialized task. Task means how I can give. Like for example, I can change my tone. So if you consider me as the SLM, so today I talk in a, or maybe as I mentioned, I am not a very good manager. I can become a good manager by fine tuning because it's the language, it's the professionalism which is required, right? It's the emotional EQ बोलता है ना, managers are good at EQs. So you should have, you can tune it for becoming a EQ, good EQ, but you cannot tune a man like me to become a doctor. So many of us who think that fine tuning can create a new domain language models is incorrect. Okay, so it will learn little bit, one, two terms, three, four terms like that because of fine tuning. But you cannot make it completely. I can never become a doctor. If I am the SLM, you can never fine tune me only fine tune me and make me a doctor. Okay. But you can make me a manager. You can make me an very good architect. Okay. Or you can make me a maybe another one similar professional or a software engineer, maybe, right? Or you can make me a mechanical engineer, which is a general stuff for me. But you cannot make me a because I already know mechanical engineering. That's why I said because you cannot make me completely different field. I cannot become an electronics engineer. So I can become a mechanical engineer, more better mechanical engineer, more better automobile engineer. I can become a better architect. I can become a manager, but I can never become a doctor or an electronic engineer, all those things. So remember this. It's a very big misconception that okay, you take a small LLM, a small means small LM language model, and then fine tune it to learn a new subject. No, it's not possible. Okay, you don't trust that. You it is maybe possible for fun work, but you cannot put that into production. Okay, for production you need more confidence. Okay, and state space model is something very, it's more of, I'll tell one thing. So in transformers, oops, okay. Hmm. In transformer, okay. So what happens is there are two processes like you say training and inference. Okay. So training here, what we mean is the pre-training part, like the main transformer. So the transformer, you have the architecture, correct? So people have made, okay, 32 layers of decoders. Okay. Then you do a language training that is called pre-training. Okay. Pre-training. So you can do parallelized pre-training. Okay. So you can do a parallelized pre-training because of the architecture of that is the main important point why transformer boomed so much. Earlier, RNN did not have that point. The RNN did not have the training took so much time and so much computation is required, right, in one single GPU. But here you can parallelize, so this training is faster. Okay. But inferencing, you have to do it in one GPU, right? So until you have a very big company where 100, you have 10, 20 GPUs, you can parallelize. But if you want to take it to your laptop or your one GPU, then it will be little slow. Okay. So it will depend on again the same number of GPU if you use, then it's fine. But for training is a big work. That's why no small companies can do a pre-training of a big LLMs. Small LLMs you can do, but big LLMs you cannot do. That's why big companies do it. Okay. So this cost is very high to do this. But you can pull it and then do an inferencing. But you since you pull it, you cannot have a lot of GPUs. That's why you cannot train it. So you will have slow inference. But that's why big companies they uh, do inferencing in their own GPUs. Okay, so this is slow. But in RNN, if you see, this is also a little bit slow. No, not slow. This is okay. Okay, this advantage, this is low, this is. So you see, this is an advantage, this is an advantage, right? So during training, LLMs are very good. And during inferencing, RNN logic is good. So using both, there is a model called SSM. This is selective state space models. Okay. So we call it as SSM. It's more of selective. So it's based on linear RNN. We are not going into deep on this because we are not using anywhere currently on these things. It's it's not so much mature and not proven. There are a lot of what do you call uh, um, confidence is not so good compared to transformers. Okay, so it's based on linear RNNs. Okay, so it can be parallelized during training. They parallelize, so there is speed is there, and during inferencing, it is just a linear inferencing. So the inferencing is also fast, but the quality is not so good. So that is why it's not. It does not bet anybody. So, but Mamba and Jamba. Mamba is the original first one. Jamba has Jamba is if you want to know about it, you can read. But Jamba is just a mixture of Mamba and some of the transformer layers. Like Jamba is, if you take this is a Jamba, so you have like this is one Mamba here and one transformer here, small transformer layers. Okay, so then again Mamba, then Mamba. So you wanted to use the efficiency of transformer because of the self-attention logic as well as the speed of Mamba. So it is like trying to optimize, coming to an intermediate way, but can we achieve better? So that is what is the Jamba. Okay. So basically it is about linear RNNs. You can go and read about it if you are interested in research on this subject. Okay. So it's interesting. Otherwise, here we will cover a little bit. Okay. But we are more interested in understanding what is a transformer model, where to use what, how we can optimize for the cost and the latency. Okay. So that's what the complete requirement of this lecture is. Okay. So any questions till now? Okay, if not, I'm going ahead. So this is the dense transformers. I guess this is simple. Everybody knows this is a very big transformer, LAMS, Llama 3.3, 70 billion, right? This is open weight model. You can pull the weights and then you can fine tune it if you want it. Okay. So, but these are all proprietary ones. You don't have the weights, but you can still use their APIs, right? These are all big ones. It can do almost most of the general requirement, general, it can reply to general queries, right? Which are mostly available in internet. So that's the point of all these LLMs. So most of the LLMs, like bigger LLMs, can answer your. I'm talking about LLMs. Okay, please understand. I'm not talking about the app. Gemini app is different. The web app is also different. What I'm talking about is the LLM. So if somebody doesn't understand the difference between LLM and H, like for example, GPT is different from Chat GPT. Okay, GPT is different from Chat GPT. Do you agree? Anybody disagrees or having confusion? I'm not saying you should know. If you do not know, ask me. We can discuss in a bit. Everybody understands these two are different, right? Correct? Okay.
Yes. Yes, sir.
Okay. Good. Okay. So that's the point. So here what we are talking about is all LLMs. Okay. LLMs can answer whatever they have been trained of. Okay. So like for example, there are stages, right? So you would have learned it in your transformers also. So first part is you prepare the model architecture. So this big companies do it. So LLM training, nobody can do it from our side, okay, until it's a very tiny LLMs. There is something called tiny LM. Somebody I think recently released. You can train this in your collab notebook or somewhere. Okay, but you can train it very little bit only. Okay. So, but why this training may not help so much is we'll discuss that. Okay, first we will consider this is the architecture. Okay, so architecture is what we are talking about the decoder blocks, right? So, how many decoder is there? What is the decoder? Inside decoder, how many attention heads are to be there, right? And what should be the dimension of the embedding layer, right? So what are all the and how do you put the position encoding into it? So either you need a positional encoding matrix or you can use rope method. Okay, so these decisions are the architectural design. So this is the first thing. But this is the skeleton, correct? So now what you will do, you will take this model to pre-training. So pre-training is what you have to do. Pre-training is the general understand. Now you are giving a life to it. So that's the skeleton body, right? This is the body. Model architecture is the body. So you are giving life to it by doing a pre-training. So how do you do pre-training? You take some data. I will not say good data. You take lot of data. So lot of data means you try to uh, give quality data. But if you are say like the same thing like earlier I discussed, right? So when you are creating a RAG flow for 10 documents, it's so simple. It's so simple. Nowadays, even BTech first year students do it. Okay. But if you are creating for 50 documents, that is also simple if you have not followed different formats. So only PDF is again simple. If you are considering Excel sheets, docx, PPT, PPTX, .txt is the simplest one. .csv, .xls, .xlsx, .jpg, jpeg, .png, .md, what else? .ml files, .py files. There are a lot of formats. So when you go so many formats and have some 100 files in each format, then comes your real engineering capability. That's where you enter into enterprise, right? So business. And now what I said was 100 of each, but now consider thousands of each. That comes the real business question. That's where the uh, big people get stuck, including me. Okay, I am not big people. I am a medium people. Even I get stuck. Why I said big people is not about me. Big people is I'm talking about the big companies who have done the model pre-training, who have a bigger LLM. Even they could not solve this. If they could solve this, then no, none of us are required to prepare RAG platform. Everybody, we can just go to big people and then get their services. Just we feed in documents and they'll give us the chatbot, which will work 100%. Nobody can guarantee that. Okay. So even you go to big people, there are a lot of big RAG models, including like earlier I used to RAG, some Microsoft service, A search is there. So you go, you will get 70 to 80. Nobody will guarantee you 100 there. Okay. Even do you do anything, any optimization, nobody is guaranteeing you. So after doing this pre-training, so what is the model look like is the model now will be able to speak good English. Like for example, you take this, this is a lot of English data. Okay. So now the model will be able to speak good English. Okay. Because it has read lot of books. It's think like a human. Like my daughter reads a lot of books. I think she would have read a lot of books more than all of my lifetime what I've read. So she reads book a lot. So she knows better English than me, right? So that is what is uh, model will become after this. So the raw LLM, what we say, it knows to speak good English. Okay, so this is this stage. Okay, generalist. But like you say, my daughter has read a lot of books. She can speak good English. Can she teach in this class? No, right? Because she needs to learn some specialization, right? That's where the next step comes, right? That's where the what do you call the? I forgot what is that. Oops. Can somebody guide here? I think it is structured uh, fine
SFT,
tuning.
sir.
Okay.
Yeah.
Ah, SFT, structured fine tuning, right?
Yes, sir.
Correct. Yeah, structured fine tuning. Yes. So SFT. So SFT is where you are trying to tell the model. Now, this is a generalist. Like I don't want to offend somebody. Okay, I'll not say the city's name. When I went there, a lot of people they speak very good, like too much English, right? So I'm from a village, so I used to think, oh my God, they are all say great people. Karke. Then as I grew up, when I became a like when you become good at some subject and the work what you do with your hard work, then you will understand that all those people who are talking so good English were talking bakwas, right? So not pakwas, the uh, crap, right? Whatever you want to say in English. So it's like that. So this is a generalist, but of no use. So structured tuning, fine tuning is what is required to make it to learn some way of answering. Okay. So that is called, like, for example, you are trying to make it to speak in instruction following way. So you give a question. So here, if you give a question, it doesn't know what to spit out. It will give you next word, but it doesn't know to answer it in a very correct way. So if I ask you a question, you answer, right? So, but this generalist does not know. It just knows to spit out the next word, next most probable word after your last word in your sentence. So, so if this was your input sentence to a generalist, it will give you the next word, which is the most probable word what it has seen in this lot of data. Okay, it doesn't know whether that makes sense or that gives a like a in a structured reply or not. So what we do in this structured fine tuning is we give structured instructions. Okay, structured instruction means I ask, okay, what is your name? Means you have to tell, okay, I'm Bhagath. So, and if I ask, okay, tell me about yourself. So I should say that, okay, I have to talk about my history, where I studied, what I worked, what all job projects I did, all those things. So that kind of questions, suppose I can make some 3,000 questions and answers, questions and responses. Okay, so this is the pair of 3,000 pairs of questions and answers I can give, and then I will tune this, fine tune this to make it structured way. So now I will get the instruction tuned model. Instructions tuned model. Okay, so now it is ready for a chatbot. So because it knows, okay, if I send a question, it will consider it as a question and it will give an answer. So from where it will give an answer? It will give answer from here. So it has read a lot of books already as a generalist, but it doesn't know how to form it, how to speak. Like it always happens, right? I don't want to offend any freshers here. So when they come out of the college and they just come to the corporate, they'll talk as if completely differently. I don't want to exactly specify that. They talk very informally. So as they grow into 2 or 3 years, 4 years down the line, they'll learn slowly. So because they see others do it. So that is called structured fine tuning. But their core value, the core intelligence, what they learned in their college will remain. Okay, that is the generalist knowledge that will remain. But this, the way they respond, the way they answer to a senior or the colleagues differ. That is instruction following, right? In corporate, we have to do. It's not only corporate, everywhere. Even to your mom and dad, you should speak in a right way, right? So if you talk like very randomly, that's not right. So now comes, there is nothing here. So instruction fine. So then comes your, so now is your instruction fine tuned model. Most of your LLM or SLMs are either available at this point in your Hugging Face or at this point. Okay. So you have to understand which point you are picking the model. So you have to see whether the model is you're picking for further fine tuning is at this stage or at this stage. Okay, that is your duty before you go ahead with the next work. So if it is this stage, then if you wanted to have do this, then you have to do this. Otherwise, you can consider that this as this stage. And then finally, what we normally do, this is available for the general public. Okay, so this part, this training, this is called actually fine tuning. So which we call as fine tuning. Okay. So this is the chatbot. This is useful for chatbots. Okay. But this big companies do it and then deploy it. So this is what if you go to Hugging Face or anywhere, right? You'll find GPT instruct. GPT instruct means this stage. Only GPT may be here. Okay, I'll not guarantee that, but maybe here. But if it says like GPT instruct, then it is somewhere here. Okay. So it knows to follow instructions. Okay. So this is the fine tuning what we are talking about. This fine tuning is a very, very minimal fine tuning. It is like your this is if you are this is the search space, your model weight suppose is here. Okay. And in the during this fine tuning, the model weight maximum will move to this point from here to here. Okay. It looks like no change, right? That is what I was talking about. It will not at all change. That is why you don't consider that this fine tuning is to change your model to talk in a different domain language. It's impossible. Okay. Okay. You can make it to speak in a specific way. Like you can. So here I was talking about instruction fine tune. Like we are talking about like, this is the fresher, right? A college fresher who comes into the company. This is like after 3 years. Okay. So this fine tuning is something like he should talk more like a software engineer, right? Not like just a corporate guy. Right? Software engineer talks a different way. A mechanical engineer talks in a different way, right? So the languages are different. So that is what is this fine tuning. So it's not like this fine tuning will take you from an engineering company to a medical college doctor. Okay. So that is what is you should understand here. So all these are LLMs, and I guess I have spoke about SLMs also at this point. Anybody didn't understand this point? This is like you can talk about as a life of a model. Okay.
So when we are saying in the Hugging Face, the models majorly will be in this category two subject section. So is there any way to
Mhm.
figure it out? Like the model is at which stage?
Yeah, yeah. You have to see whenever you pull a model, you should read about the model. They would have given a big documentation with that model, right? They would have told what is the lot of data. I was telling lot of data, right? They would have mentioned what is that lot of data, what are all the data they use to pre-train, and what whether if they would have done the structured fine tuning, what is this data they have used for structured fine tuning. So these things you have to read before understanding what you have in your hand before you proceed to do what you wanted out of here. So this is the model you wanted, right? So before you go here, before you start doing this fine tuning on this model, to understand what are you having in your hand when you pulled it from Hugging Face, go read about this, go read about this, and go read about this architecture. If you do not know these three things, you will never succeed in a good fine tuning. Simply pulling a model and fine tuning will never work, right? Because if it has been trained on a biased data, on some, for example, best example I will tell you, most of the companies are either Chinese or US people, right? So you pull a model of Western, US model, and then start fine tuning for Ayurvedic queries and response. So you have to fine tune so much to avoid those kind of biases, right? You have to come out of it. So I'm not saying that they are not interested in Ayurvedic or something. I'm just trying to give an example here. Okay. So which is more of Indian origin. So this lot of data would have never covered that. This lot of data would have never covered that. So how can you do this in a more precise way? You cannot make it, you learn the terms, right? First of all, that is a different domain, even though that is more of medical. So you'll take about a model which has been completely trained on medical books. Lot of medical books it has got trained. But you may not, it may not get trained very nicely on your Ayurvedic data, because medical books generally are more of allopathy, right? So when you want to train or fine tune that model to this one, it will be very difficult for you to get good results. So if you can do this pre-training, that will be better. So pre-training only will make it learn the stuff. This is where it learns. It just fine tunes here. It gets structured at this point, and it gets fine tuned here. No learning, no learning. Sort about, like, it's very little learning is there. I'll not say zero learning. It will learn. People will bet on it, but you should not trust on that learning. It's not in a production grade learning what they will learn. The production grade learning happens here. So you have to pick the model correctly for your particular domain. So if you want to speak about, if you want to deploy a model for your financial company or model, so you take a model which has been pre-trained on a lot of financial data. So go read about the LLM or SLM, and then understand what is the lot of data, the pre-training data, what they have used. If it is more of finance, then you have chosen the correct model to do the further fine tuning. That's what I would try. I hope I answered you. Right? Lot of circles. Okay. Am I clear here? Did I
Sir,
answer your
I'm just
query?
Yes, sir.
confused between structured fine tuning and instruction fine tuning. Like, what's two things we are targeting in these two blocks?
Where is instruction fine tuning? See, structured fine tuning is the process. This is the model. This is the output. This is not a process. This is the output. This is not a process. This box is just the output
Okay, okay,
of this process. That's what I'm talking about. This is one process, this is second process, and this is the third process. This is the output. So this is the output. Okay, this one is output. I am using mouse. This is an output of this process. Okay,
okay,
got
sir.
it? Hmm.
Yes.
Hmm. Okay, we'll move to the next one. Oops, never chala gaya. Okay. Uh, the mixture of experts. So it's very easy. So if you understand the this one, what do you call the linear layers, right? So if you see, there are where is the diagram here? Okay, no problem. Diagrams are not there. Just give me 1 minute. Oops, I should have added a diagram here. Hmm. Hmm. Oops. Hmm. Okay. So can you see this, right? So this is a very good this one. So if you see just that only one thing I wanted to show here is that so you're not splitting the attention heads. Attention head is same, okay. But the MOE block is that non-linear block, the non-linear, what do you call the non-linear feed forward network, right? You agree that this is a non-linear feed forward network. This block has a lot of experts here like this. Okay, here if you see there are 16 experts. So in the regular transformer, what happens is after this layer normalization, okay, so it feeds into this uh, neural network, right? That's a simple feed forward neural network. The complete layer is used. So for example, here if you take, so after this is your input and this is your multi uh, self attention, multi-head self attention. Okay. So after this, all these skip connection you can have, okay, layer normalization. After this, what you will have is this complete feed forward network. Okay. So this is what you will go. Yes, again, there is a skip connection. Okay. So this is a complete neural network like this. Neurons are like this. Okay. So that three lines are something like this. So this are all the embedding size will be there like this, and then there will be a so there are three layers, for example. So the suppose this is the embedding size 768. This is 768. Maybe this is 300 something, 84, something like that. Okay. So there are 384 neurons at the middle layer. Starting is 768, ending is 760. This is one complete neural network. Okay. So, but what in the other case, what we are doing in the MOU case is like we are creating a lot of experts. So this is a little bit confusing. It's better I draw it here. So instead of this one, what we will do, we'll take one same multi-head self-attention is there. Okay. And after this, what we do, instead of one big neural network, we are creating a lot of neural network, small neural network. Okay. So what happens is there is a gate here, router. So each this router will decide. So it's normally two. So two means this is the router what we are talking about. The router is like it will take the D and then divide it into number of experts, right? So number of experts means I'm taking that two experts. So here K is two means I have to select among these five any two. Only two. I'm not going to process it completely. Okay. So in this, what happens is I am saving the inference computation. I'm not using half of the parameters at all. So and then I combine this, and this is not every time the same two, right? It again every time every token is processed, right? In transformers, you understand for every token it goes through the complete process. So this router will decide which of this five out of these five, which two blocks it has to pass through. Okay, so it will decide and then send it. For every token, it will decide depending on that particular context. It is not even dependent on particular token word, a specific token word. So it will again depend on the complete input sentence. Okay. So whatever, so for this token, it will decide maybe this two it will go. For next token, it will decide, okay, this and this it will use. Okay. So that is what there is a linear layer to give which token. This is the number of experts. It will design which of the expert it is going to use, and then it will send the D to that two numbers only, so that remaining these three are not being used. Okay. Now point here is there is a issue here. What is happening is like sometimes during training, what will happen is most of the tokens might take these first two. These might get little number of tokens to go here. Okay. So what they do a load balancing. So load balancing, what does that mean is uniform distribution of tokens across experts, which means during your training process, for example, I take a batch of suppose 128 inputs. Okay, so you understand pre-training, right? So I guess you would have learned it in the how this pre-training happens. So if you guys understand, then you can understand this faster. Otherwise, you consider that, okay, 128 input samples, okay, for which I have to produce the 128 output samples. Okay? That is one batch. For that particular batch, what they do in this auxiliary loss logic is that they will equally distribute for each of the five is not correct. So you can consider, suppose 125 is the batch size, which is not normally. I will consider better is 8 here. Okay. So, 6, okay, 7, 8. So consider that 8 uh, 8 branches are there. Okay. So 8 branches are there. So if you consider 128 is one batch, so you divide by 8, and then whatever you get 16 tokens should be using each of them. Each of the blocks should get 16 tokens. That is what their idea of training. So what happens is you're like trying to cluster this 128 into 8 batches, 8 clusters, not batches. This is one batch, and you're clustering it into 8 clusters. Okay. And then that's what is the idea behind it. So you're forcing the tokens to get um, distributed for each of the this blocks. Okay. So that's the idea of this load balance. During training, we are trying to distribute it, because what they found it during training without this load balancing, what will happen is like maybe this first 4 is always mostly used. Okay, so the second 4 is not at all used. Any token, if you want to like give as an like produce output for any token, only the first 4 is always used. This last 4 is not at all used. Then what happens is two problems will get issued. One is, the first issue is that so half of your network is not used. Second issue is that your load balance also will be less, right? So for example, you inferencing bigger models, they'll do like maybe each one they are putting it in one GPU. Okay. So if you see, this 4 GPUs will get lot of load, and these 4 GPUs will always remain like uh, idle, right? So that is not good. So for design purpose also, it is not good. So there'll be a little bit of this is like we are trying to force these 16 tokens into one new block. So that is a bad thing, but it doesn't affect so much. That's what they have seen it. After you train for so much time, it accommodates. Okay. So that's the point here. So for example, in the Mistral, if you see 8 into 7 billion. So each of them has eight experts. Okay. So each is 7 billion parameters. So total is 48 billion. So if you say like 2 blocks are only active for per token. Okay. So top 2 experts per token. So only this much of your what do you call? This is the reduction. What I'm saying is only these many number of parameters are or computed at a time. So ideally, if you have the computing and calculation, so you can consider around 2.5. So it is 26 plus 6. So 32 GB RAM, this is sufficient for this model to run. So even though this model is around 56 GB, 56 billion parameters, which is around maybe so much of this one, but for running this much RAM should be sufficient. Okay, that's the point. Okay, and this is the same logic here, the same thing. So this is
32
a simple
GB,
calculation. How this 32 GB came? Is that the question?
2.5 times you did, is it?
Yeah. It's a fair, it's not any calculation. It's
Yeah.
a fair calculation. Ideally, it is around 1.8 also, 1.8 times also will be fine. But to be more precise, like safer logic is 2.5 times X will be safe for deployment. So whenever you want to pull a deploy a model, consider 2.5 times of that VRAM. That should be sufficient. Okay. Yeah, these are all same logics, same thing extra. And now coming to smaller language models. Okay. So smaller language models we have already seen. So this is Gamma 2 billion, Phi, Queen model. Okay. So all these are uh, mostly all are general purpose only until if they have specifically fine-tuned that model for a particular task, like what we are talking about, that SFT, right? So if they have trained that SFT and for a particular use case, that's why you have to, whenever you pull the model, read about your documentation. That's the right thing, right? So as software developers, you should read documentation of every library, right? So read about it. So model also you should read. Simply don't see internet and then take the model. Okay. So go through the data, what it has been trained in, and what are all the training steps they have taken. Only pre-training or SFT, or some people they do reasoning also nowadays. Okay. So apart from SFT, they will add reasoning fine tuning also, RLHF, right? Correct. That also they do. So and finally, those are all available. That is why you will. So it's not like that. Gamma is not. Uh, what do you say? Gamma is not a good model. Gamma is like maybe it is only pre-trained. So that is more good model for you. People think that okay, Phi is maybe better model. I'm not saying this specifically. I'm just saying that one LLM is very good at coding means Gamma is bad. So this is like innocent people, layman's language. So you should understand Gamma is it is just only like consider this case. General purpose means they are only pre-trained. So they have given you more freedom to make it what you wanted. That is more good than going for a model which is coding model, right? Until you wanted that coding as your requirement. So if coding is your requirement, then you can pull this. But again, you have to see whether it has been trained on Python code or it's C# or Java or whatever it is. So any model you pull in, you should learn the data, how it is trained before you use it, right? It's so everything it is applicable, right? So even before you choosing this MTech degree, you would have studied from your seniors whether it is specifically useful for your particular domain or not, right? Same way. So do that and then understand what is how you have to go ahead from there, that point. Okay. And safety tuned means guardrails. So this is more good. General purpose safety tune. You can deploy it on enterprise. That's the that's the point you have to take from here, right? So Gemma, if it is safe to do, you re-verify it. I have written here, but re-verify it in the documentation of them, whether they have done, and in even if they have done safety tune, means guardrails fine tune, you have to see what all guardrails they have taken in. So we will see that later in our course, what all guardrails requirements are there, right? So whether all of that has been trained or it has been trained only on few of them. So, so this model is more safer than this model for production grade, right? So you can take this model and then because guardrails is a general requirement, right? So you deploy it anywhere that guardrail is going to be useful. So somebody who has trained it on guardrails will be more good model than somebody has trained only on code. You understand? Code means which we like bad things they would have written. Who knows, right? You don't know. So whatever it will give comments may they can anybody can write anything, right? So maybe some names are written in the comments. So you cannot pull a model which are only trained on code solely. So I'm not specifically mentioning this model. Maybe this model also has been trained on quadrails. Any model you read about it completely, understand, and also you check there. That's why benchmarking you have to check, right? Benchmarking check. That's a very big process. It's not simply pulling, okay, I use schema today. Oh, it's not working. Let me use Llama. I have heard this from many people. Simply they will go and try like, what do you say? Trial and error. Yeah, we are all engineers, right? So we have to be more precise on what we are doing. So that is why when you understand its processing training, then you appreciate why we have to see all these things. I'm not saying wrong who have done, not done. It's just that they do not know how this is working. So if you consider completely black box, then you will consider that, okay, today I will try gamma, it is not working. So let me think of llama. Why we are going for gamma? Why we are going for llama? Nobody knows. Simply, I tried llama. This is not the correct answer, right? So keep that in mind. Okay. So I hope you guys will be more educated. That's the purpose of that, right? Purpose of this course beyond all these equations and all stuff, right? So, and attention mechanism you have learned. Just I wanted to give here why, because it will be useful for the next
So
slide.
one
Okay.
question,
Yeah.
one question. So
Hmm.
regarding this gamma and llama, you said, right? If I
Hmm.
am intended to train something with respect
Hmm.
in gamma or llama, is there a way to identify that the learning uh, pace of llama and gamma, right?
Hmm.
What will be the learning pace? Whether llama will be able to learn quickly and adopt, or gamma, how we will evaluate that? Is that
By
possible?
seeing the original data, no? So original data, what it
Mhm.
has been
Accuracy,
pre-trained.
is it?
No,
Okay.
accuracy nahi. Pre-training
Mhm.
data. See, first
Okay.
of all, you have to see the pre-training data, what I was telling here, right? So if you
Hmm.
understand what is the pre-training data, and this distribution matches your personal data. So the data, what you are going to fine tune this, correct? So this is, I call it as personal data or your domain specific or task specific data. Is the correct word, I guess. Task specific data. So if this distribution matches with this distribution, then you can go ahead for fine tuning and this will learn better. Okay. That is one thing.
Okay.
Second
Okay.
thing is how good is your specific task specific data also. The quality of the data. If it also has a lot of confusions in it, like you are trying to get a lot of work from it, it will get confused. Always have task specific data in a very less of what do you call the clustering. So like if you do clustering, you should maximum get two clusters out of it. You know K means, right? So when you do K means, you should be able to get two K means only maximum. If you can get one K means, that is best, but you should not get more than two K means. If you get more than two K means, which means your data is too much of variety. So then it becomes more confusion for the model to learn. Then you have to go for bigger model architecture. Okay. If you want it
Right.
to
Right.
learn better,
Mm.
then you have to go for a bigger model. You cannot trust on 1 billion or 1.5 billion. Okay. So
Okay.
like,
Okay.
okay. Yeah. So coming here to the attention mechanism. So this is the formula, right? So you all, everybody knows. So what we are trying to say here is, so this is the slide you have to understand. So if you see, transformer has quadratic complexity, right? So you understand that, right? So if you see, you have to calculate that Q and K. You calculate the mechanism, right? QK, this one. Okay. It's already there, I'll not write. So QK, when you do, you are calculating this n into n matrix. You agree? So if there are n number of tokens in your input, okay, this is sequence length. So the number of tokens in your input is n, then it has to calculate this QKT, which is a n into n matrix, right? This is called, what is this called as? It is written somewhere. Somebody knows? What is this matrix called as? Attention matrix. Okay, no problem. Attention scores. Okay, so attention matrix we call. Okay, so that matrix you multiply with K, right? So that is what is here. So when you get this QKT, you multiply with the K. Sorry, not K, sorry, V. Okay, so sorry. So you QKT, you will multiply with V to get the final matrix. Okay. So point here is to calculate this n into n matrix. It's very memory requirements are very high. So if you say for a sequence of 512 tokens, it's these many number of attention scores have to be calculated. And for this, you see, it keeps on increasing so much. This much amount is getting calculated. That is why it takes so much time, right? And we feel that these are all important, right? So I don't disagree with that. That is why we are getting so much. That's why we are like better than the RNNs. RNNs did not do this much calculation. That's why it was not so good. So this is the improvement what we did from RNN. Okay. So grows quadratically. So for long documents, it takes more time. So that is why even if you see in your LLM calls also, when you give a very small question query, so that's why prompt optimization is very important. So nowadays, very big context came, right? So the concept came, context engineering. So what is context engineering? You give the context to the LLM as minimum as possible, but with high quality. Like you guys can go and read about this also. If you guys are already working, so there is a recent one. Instead of JSON format inputs, you can choose tune format. Okay. So this is more optimized format for LLM input context. Okay. So earlier we used to give JSON format and we expected to give JSON output. Okay, that's more of structured. I think next class we'll discuss that. But I'm talking about, we'll discuss this maybe next class also more detail. Okay, this LLMs we can use tune. So why I'm talking about this is context engineering. This reduces lot of tokens actually. Okay, so but still it follows a good accuracy. It has not been tested into production, but this is good. Okay. Recently I read, I think 1 month before onwards, it's quite famous. So what we are trying to say here is it's very we have to when you give a very big prompt, like what happens in RAG, I have seen like uh, they give like whatever context they retrieve from using RAG, they just dump it on LLM and then say, okay, how much ever you want, you give it to LLM and then LLM will find the answer from the book. So you give the complete book, right? So if you give the complete book, then you have to wait for the LLM to read the complete book. That's what is this quadratic nature. So you have to wait that much time to. It will surely read. It is not like Gemini. You take, so it has around 1 million or 2 million context window, right? So it will all whole of your book it will take, and it may give you the correct answer also, but you have to wait till it calculates everything. That's not the production grade solution, right? Production grade means you have to get it faster. Cannot make your user wait for 10 seconds. He will think that your server is crashed. He will leave the place, right? So even though your circles are going on, right? So that's the point. So what happens is there are some thing. One is that state space model, which we discussed, right? So state space model does linear RNN logic in a selective way. There's a one thing called selective. And the one more thing, if you want, actually, you don't need to remember the equations and all, as I already told. So just understand it uses complexity. The only thing you have to remember for exam is this part. Okay. So instead of this, it is this. Okay. Sequential state combination, this also okay. You can only whatever there in the slide you should learn, not only this part. All these 4 points you can remember. Okay. Linear time scaling. It's same thing as this point in like filling the pages, writing the same thing in different wordings, right? So that's the point. So point is how architecture wise, this is same as linear RNN. Okay. So you don't need to know more about it, but this is not very good accurate model. It doesn't give very good results. Okay. So what we do, we have to go for a some way to optimize our, what do you call, the transformer itself. That's what we will see next. Okay, before that, we will see what is there in this slide. The same thing, whatever I talked about. Transformer is quadratic complexity, expensive for long sequences, but this is linear complexity. So because the equation is also linear, if you see. So how this is calculated, you want to know. So it is like X you will take, this is the input. Okay. So it creates for every input. So input, this is first token, second token, third token, like this. Okay. So it creates three values. So it finds A, B, C. Okay. So A, B, and then delta. Okay. Delta is this D. This D. Okay. Write D only. D. Okay. And then it then what happens? This is the learning part, and then you will get this for every token. Okay, so every token will get this. This is learning the context of that particular word. Okay, then what happens? You combine this and like in CNN, what we do, right? So with small window, not all the words at a time. So maybe three words at a time, and then these three words next time. Okay, so you this is like kernel logic. You understand the kernel trick. So you learn if you know pixels, right? In CNN, you would have learned, right? So you take this part and learn it. And then you move to this part, you learn it. Sliding window concept, right? So you keep on learning like this. Correct? So and then what you will get a smaller image. This one would have gone to this part, this one. And this next block is we'll draw it in next this color. This is your second block, and this is your second block. Okay, and third block is suppose this is your third block. Oops, sorry, same color. So this is your third block, and this is your third block, like this. Okay. Similar way, the first three tokens go into like this, and then so it is learning in window basis. Okay, so in this, what happens is they will just learn this ABC only. It doesn't learn anything else. It just learns A, B, C, D, these four parameters. Only these four parameters for different layers it learns. And then whenever a new input comes, it produces an hidden input and then goes into this part is the nonlinear part. This is the nonlinear part. This is like linear part. You can parallelize this. So that is the difference between RNN and here. In RNN, you cannot parallelize this, but you can parallelize here. So these things you will calculate and then you will take it to next hidden layer and finally to the last YT. Okay. So very simple logic, but point is since you are using this kernel trick that CNN logic, you are trying to understand the this word based on this word and this word. You understood, right? So at this point, what we are trying to learn is from this word, you are trying to, so you're combining these three words into this. And in this block, we are trying to combine this word and this word and this word, correct? So like this, next time there is one more layer, this word and this word you combine and you. So at this point, you will learn the complete architecture. So and then you can try to produce the next, what do you call the next word. This is also next word prediction, right? So you'll produce the next word. Okay, this is a very simple thing. You don't need to learn this architecture. Just I wanted to give an idea about it. But other than that, you can just understand by where it is can be used. Okay, so currently they are claiming that long documents it is good, but my point is I'm not sure whether it is good or not. I have never tried it. You can try and check. Okay. So this is available for usage. Okay, that's what one thing. But LLMs are better in that because due to that self-attention logic. That is why this Mamba has gone. This was purely what I drew here. Okay, this part. But in Jamba, that other one, no, it is not mentioned. It's called Jamba. So in Jamba, what they did, they made blocks. So not just one Mamba, like Mamba is here, and then there is a transformer block here, so that this learns that uh, good that quality point of that transformer side. The transformer advantage is learned here. Okay. Second a Mamba, then the transformer, then one more Mamba, then Mamba again, then transformer like this. So I think 8 layer they have. You can go and read about this. So in this case, they say that they have improved, but again, this will be a uh, like blocker. Blocker means what you say, it will increase the time, but since others are faster, so they are trying to optimize the advantage of this and advantages of this. Okay. Hmm. So now coming to the model routing. Model routing is bit different from the MOE model. MOE model is inside the transformer you are routing. Okay. So the complete model inside that you are routing. But in model routing, what we are doing is we have a simple task. Okay. We have a medium task. We have a complex task. Like I already mentioned this, like for example, in your mobile, the Gemini app is there. Okay. Gemini app is there. In that, if I say hi, do you want Gemini 2.5 Pro to answer this answer this hello Bhagat, something like that? If somebody says hi, I should say Uta. So if the user says hi, so the user says hi, so it should reply hello or hello Bhagat, something like. Do you don't want a very big model to do that task, right? So you should route it properly. That is called model routing. So once you get the query, so in our conversational logic also we have seen natural language understanding. This is the first step of any conversational system. Okay. So once your query comes in, you send it to this model. So either you can have a DL model here or a ML model, or nowadays a small SLM. So SLM can also do this. So put a small SLM there to identify whether SLM itself can answer that question or not, right? So SLM का instruction में you can tell either if the question is completely answerable by you, then produce the answer. Okay. So this SLM can do multiple things. One is it can act as a guardrail. Okay. Guardrail. Plus it can answer greetings queries. Correct? Greetings queries. And it can answer guardrails will take care of unethical, illegal queries and greeting queries. Then spelling corrections. Okay. So these things it can handle. So spelling correction is actually I should not write here. Uh, so guardrails is something like queries, right? Query type. So when there is an illegal query or unacceptable query, it should simply reply to the user that, okay, I cannot answer this query. I'm not trained to do so. In a professional way, you say, get lost. Okay. And for greetings query, you can easily say that, okay, hello, Bhagat, something like. For all other queries, for which maybe another some queries like simple queries, simple English queries, maybe uh, what is the life expectancy of a human or something like that, which is a very simple query. I don't know what's a simple query. What is the color of sun or sky? General queries, which are a small SLMs can answer. Okay, so very general minor queries, correct? So which can be replied by this SLM completely. That's very important. Your instruction should be very clear, which can be answered by this SLM completely. Those also can be replied. Okay. But beyond these three category, then it will route it to the next stage, the next big LLM, whatever it is, either this LLM or this one. Okay. So either it can route it to here or it will route it to here. Okay. And while routing, you can, so this is like either this answer or this answer or this answer, or while routing, you will do the spell corrections. So while routing means before it goes to medium task, you are giving a better question that is called query enhancement. Actually, I'm writing it as a spell correction. That is called query enhancement. Okay. Some things like sometimes I normally very poor typing. I'm not a core software guys, right? So whenever I type, I make a lot of mistakes. Like please, somebody will miss like please chhod do. I never write please there. So suppose like for example, uh, mm, ah, uh, classification. So I write only one S. So this kind of mistakes we can change, right? So this and all query enhancement. Then you can also do query subquery generation, you know, subquery generation, all these things. So once the SLM is not able to answer these these way in this way, then it will try to route it with query enhancement. Now I have told so many things. Not every SLM can do all the things. Okay. So sometimes SLM can only do the guardrail check, or only do the greeting stuff, or only do the general one, or only do the routing. That also you should be clear. It's not like that I have told that you don't claim that, okay, sir, SLM, I have given all the work to SLM. It's like asking a 6th standard student to teach ALML, AML, right? So if that is why you should learn what this model has been pre-trained for and what it is benchmarked for. Two things, whenever you pick a SLM, learn about its pre-training data, okay, and the model architecture, of course, okay, that is by default. Third one is the, I forgot, what is that? Benchmarking, benchmarks, or on data sets, right? So you understand, right? This one on various data sets and which data set you want to use, right? So that you, so check on all those things. That's called model routing. Okay, so I think this page is completely covered. So we are seeing how models differ in architecture and scaling. Now let's see how these choices. Now coming to the cost part. Okay. So any queries still here? Are you guys learning something?
So one thing, sir, SLM can be converted into LLM based on training or not? Future
No. SLM is a smaller one, right? So you cannot convert SLM to small.
LLM,
SLM
right?
and LLM is based
Mhm.
on its parameters. So SLM is like, for example, this is input. So SLM has, this is the block, right? Decoder block. Decoder 1, decoder 2. SLM has, suppose, 10 decoder blocks. Okay, this is your output. The softmax layer will be there. This is your output. Okay. So this is SLM. What is LLM? LLM is you have the input, you have the block 1, you have block 150, and then you produce output. So how can you convert this here? But you can convert this here, but you cannot convert this here. This is only 10 blocks, right? Convert
Mm.
means what do you say? Like you can
So
repeat
I
this
mean,
thing.
the decoder can be increased and made LLMs like that. Infra can be increased, or
Ah, yeah,
we
that
can't do.
can be done. That is,
Mm.
you would have learned it in CNN, right? CNN, there
Yes.
is something called ResNet
Mm.
blocks,
Mm.
right? So you learn, that is how they prepare big architectures. You learn one block and then repeat that. I
Repeat and
forgot the
overlap.
exact name. Repeat and overlap. Yeah, during training, they would have done that like that. But
Okay. Okay.
SLM, what we call is after that pre-training, right? So
Mm.
so that
Okay.
makes, yeah, that also you can do. Like you take one SLM, give the input. Like for example, this is your input, original input. Keep one SLM here. That output you will get, but this output itself will be the answer, right? So if you pass it to a second SLM, it doesn't make sense until you pass the input also and tell it to just verify, like whether this
Right.
answer is correct or not, something like that. So it's like you are making a bigger LLM out of smaller SLMs. So this is the workflow. This we will be learning.
Mm.
So this is the workflow. Yeah, this is different, but converting SLM into LLM is mm, like during training. Yes, that logic is correct.
Okay.
But in
Okay.
inferencing, it is not possible. Yeah. But
Okay.
in LLM to SLM, they do. We will learn that. That is called a knowledge distillation. We will learn that. Okay.
Okay.
Will come later. Yeah. Hmm. So quantization, I hope everybody knows this quantization, FP32 and other things. Anybody doesn't know what is quantization? Any doubts on quantization? Do you know all these
Sir, I have a
formats?
query.
Yes, yes, yes.
Sir, let's suppose I one query is there. Okay, so that required both SLM and LLM. Miss query is such that it requires both SLM and LLM. So how it will be breaked? Miss one big query will be there. How it will be breaked?
Okay, you're talking about routing logic. Okay, I
Yeah, yeah,
understood your point. Yeah, what you're saying is like you have a query here, which is a suppose it has a first part one, and there's a part two. Okay, and you want to send part one to maybe SLM and part
yeah,
two
right.
to SLM, right? So that is where your
Yeah, right.
router is there, no? That is what we saw. Router is there. It will send here and here. So I told no,
Okay,
you say subquery generation,
okay,
query subquery generation. So you give the bigger query, which is a single paragraph. Okay, this is not as different. So by humans, for humans, it is a two different, not two different query. It is single question, but it has a two different requirement. Then the router, this NLU SLM, will try to understand that it cannot answer, and then it will try to route. So while routing, it will create two subqueries, and then you have to get this in structured format so that you can cut that and then send it to a individual, whatever it says, wherever it has to go. If you have a router to send it to the small SLM and a complex stuff, that is where you will get prepare that workflow. So we'll see that structured way next class. We'll have the structured part, and later classes we'll see how to create that workflows. Okay. Hmm. So quantization is very simple. I guess you guys know, right? What is this? Okay, this is more easier. So do you guys understand what are all these quantization? FP32, what is it? What is written already? So what is not written? What is BF? BF16. Anybody? What is BF16? What is the full form of BF? Dimag. Brain float. Okay. And what is FP? FP, though everybody should know. It's already written here. Correct? Floating point. So what it is during training, that training here, what we mean is pre-training. So most of the models are trained with at FP32. So you understand what is FP32, right? So what is anybody, do you know what is the range of this FP32? What is the range? 3.4 into 10 to the power 38. Plus or minus means plus minus 3.4 into 10 to the power 38 to plus 33.4 into 10 to the power. It's a very huge number, right? So that is why it is uh, this huge range of number is used for floating point training. During training, we are using this. So the whole purpose of this quantization point is that during training, you every parameter. So we are talking about like in the earlier Mistral, we are talking about 56 billion parameters, correct? So if you see 56 billion parameter, which is 7 into 8 billion, that's what we were seeing, right? So that one, you have 56 billion parameter. So each parameter is 32 bits. 32 bits means how much? 4 bytes, correct? So you calculate 4 into 56, that many number of bytes, right? Correct, no? Agreed? So I don't know how they calculate. Ah, okay, this is for 7 billion. Okay, we'll take that only. So we'll consider 7 billion. 7 billion model. 7 billion model, if you consider each parameter, 7 billion parameter, 7 billion means this is million, this is billion, correct? This much into 4 bytes, correct? 4 bytes. So 4. 4 into 7 is 28. 28 into 9 zeros. 90 means it is GB, correct? So this is 28 GB. Understood, right? So how this 28 GB came. So 4 bytes, right? This is 2 bytes. Remember this, okay? This is simple things. So 7 billion model became 28 GB, okay? So the model size is very big, right? So you cannot run inference here, correct? So inference on this again will take more, okay? So now point is FP16. So during inferencing, you can do a quantization. Quantization means you don't need that much precision, right? So you can reduce the precision. So, so if you make it 7 GB, then you may require only 2.5 times of this is how much? So 2 times, okay, 14 GB RAM is enough. VRAM is sufficient, correct? So this much RAM is sufficient for your this model. Same 7 billion model, when you quantize it to int 8, then this much is sufficient. We normally quantize it to N4, NF4. Okay. So in this case, on your laptop, RAM is sufficient. 7 to 10 GB is sufficient. Okay. So, but your original model was 28 GB, right? So 28 GB will not even will get stored in your hard drive. But while inferencing, it has to use your RAM, right? So because the computation will be there in the RAM. So that time you have to quantize it and then take it as 3.5 billion GB and then do the inferencing. So your laptop RAM of if you have 16 GB, that should be sufficient. And you see the quality difference. So this was 100% and this was only 98%. Maybe it is 95, 96, but it is fine, right? So you can do it in your laptop. That's the point. So you can do it in a lesser environment, bigger models. So like we were talking about bigger LLMs doing it, right? Take a big LLM of Llama like 8 billion, 8 GB, sorry, 8 billion. Llama 3.3, 8 billion model. Okay. So 8 billion model, if you will do inferencing, it will be like, it will require at least 20 GB. Okay. Correct. No, I'm wrong here. So 8 billion. So 8 billion means you will require 32 GB memory. Okay. So memory this much means you have to take inferencing time, you have to take twice. So it's like more than 64. 64 plus 16 is 80 GB. So 80 GB you need for your RAM. RAM memory should be 80 GB to run this inferencing on this model of 8 billion. It will be very slow. But if you do quantized, but many people do this 8 billion. How? They don't pull the complete model. The trained model is at FP32 precision, right? So what they do, they will dequantize it. So, sorry, quantize it. So when you quantize it to NF4, which means 4 bits, right? 4 bits means 8 times reduction, correct? So 8 billion, which is 32 GB. If you do 8 times reduction, it will be how much? 4 GB. Okay, 4 GB will be your memory hard drive. And when you do inferencing on this, you hardly require 10 GB of RAM. Understood, right? Got it?
Is there any
Any-
limit of this quantization or like we
I
reduce
think
by like
you can reduce more also. There is 1 bit of, there is something called 1 bit LLM released by Microsoft. It will reduce this accuracy. If you're okay with that, it's fine. You understand, right? So that's the point.
trade-off
So,
is with the basically accuracy.
correct. Because it will lose its. So it's like, for example, it's like a simple best example is your pixels, your HD, FHD, same exactly. So my monitor, if you this for this, I require 2K, right? So 2000 by 2000, like 2K, like that. So that much density is required. But if I put HD, then it will be less clear, but it will be visible. It will be less clarity. So what I want to say by that is Like for example, this is my search space. If your original model, which was trained at FP32, will be able to identify the difference between bank and bank. So suppose not bank and bank, you can take some two other words. Mm, what do you say? Mm, any nearest words you talk about? Uh, okay, you can take this only, right? Uh, int 8 and int 4. These two are two different words, right? So these two are little bit different, like because of its precision. Because of its precision, you can identify the difference. But when you will reduce it with pixels, like quantize it, this is like very nearby, or you can say this is like there are here there are two more points here, but there are no points in between. So all these points will become like one point here. And all these points will become one point here. You understood, right? So this and this are neighborhood now. There is no minor differences are not visible here. You understood the difference, right? So it's obvious. Maybe sometimes you may get int 4 instead of int 8 also. That's the idea behind this quantization. So it will quantize it. Like in your pixels also, what do you do? So when you will reduce the, when you, what do you say? When you will reduce the resolution of your image, what happens? You have originally this many number of pixels in your image, correct? So if you wanted to reduce the pixels, when you lower the resolution of your image, what happens? It will take the 9 pixels and then average it and then create one box here. So this box is an average of this 9 pixel. Exactly that is happening here. So this cluster is made as one point here. But there are some three words there. All the three words will be like a single word here. You got me, right? You understand? So the clarity, that minor differences. So it again depends on how much far you are going. So if you go from here, maybe two nearby words are merged to represent as a single word. So if you go from here to, this is same bits. So if you go from here to here, little more words are clustered into one. If you go from here, more number of words. So that is why there is an accuracy difference. But it will be far, like it is like there is something called temperature. That also, if you will make it random, it happens like this. Okay. Randomness, that exact precise calculations will go on. That is why during calculation we use 32 bits. One is for the precision, second is that backward propagation. Okay. So backward propagation, if you do with this, it will be lost completely. Okay. So that's the point of quantization complete. Okay. So point is, when you do quantization, you can reduce the size. Okay. What is this GPT? Somebody knows what is the GPT? In quantization, general post-training quantization. Okay. So right here. General post training quantization. Okay. So this is what is post training. So post training quantization is after you say so post training quantization we'll see first in the first topic, the top topic. In the top main topic, post quantization, what does this mean is post training means, what do you say? Well, I was talking about the training phases, right? So you take the model architecture, you do a pre-training here, and then you get a pre-trained model. This is the LLM, which is pre-trained. Big companies do it, right? So after this, you do quantization. This is called post-training quantization. Okay. So you do a training and then you do a quantization and reduce. So this is suppose 32 GB model was there LLM while training on FP32. So you do a quantization to NF4, for example. So what happens is this becomes LLM of 8 GB size. So you reduced the size of this LLM. Okay. So this is post training quantization. There is one more thing that for that only we are learning here. This one you understood, right? Post training quantization is after your pre training model is trained, completely trained on FP32, 32 GB memory, you will do a quantization at this point, reduce the precision of the values of the all the parameters like weights and biases, right? And all the float values of that embedding model, embedding matrix will be there. You guys know, right? So if you say in a when you give the input, what all it goes through, it takes the embedding matrix table. So there is an embedding matrix table, right? So it gets converted into tokens. The input prompt gets converted into tokens, token IDs, right? Token and token IDs. And these token IDs are referred into this embedding matrix tables. And then it will create the embeddings, right? The vectors. And this vector goes into your transformer, right? So transformer has weights and biases, which are the parameters. And then that goes the output. Okay. So there are a few more layers also, which will have some, but majorly it is this one. And then that Q, not Q, W is what all W's you have. Anybody knows what all W's? Weights in transformers. You would have studied in that DL, no? Anybody? Anybody? Okay. So this is your linear LB time, some people. So this is your QKV. This is your starting before the self attention, and this will be your feed forward network. Okay. So for to understand this, I guess you would have understood. Don't you guys know this? You would have studied now in your transformer chapter. Didn't I teach this? I think
That
somebody
was
from
very
my class.
basics. Basic was there, introduction transformer, not in depth one.
No, this is the basic stuff, right? And these are the parameters which have to be there in the transformer. I think we studied this. You guys would have missed. No problem. Uh, if you wanted to learn that more, go read about this paper. Okay, we'll go through this part next class. Mm, mm. I'll explain little bit for 3 more minutes, but again I'll go through this next class also. If you want to understand about these 4 components, go through read this LoRa paper. Okay, I think 23 it came. Okay, so this LoRa is low rank adaptation. Okay, so low rank adaptation is so this is the best example you can see. So you see traditional fine tuning. So this fine tuning where I am talking about is after pre-training. Okay, pre-training and SFT. So this is your model architecture. So you do pre-training. Okay, then you get pre-trained model. Okay, so then you do SFT. You get instruction tuned model. Okay, then you go for fine tuning. This is what you do. Okay, this is what we normally do it in companies if you wanted to do. Otherwise, you can use this model also. Okay. So whatever is output here, this model also you can use, or you can do a fine tuning and take a task specific model. Okay, this is your fine tuned SLM. And this is your SLM, which is available mostly in Hugging Face. And some people, they put this also. So this is one first stage, second stage, third stage. Some Hugging Face models are here, some Hugging Face models are here, some Hugging Face models are here also. You can take this and do further fine tuning, or you can take this and do this. Okay. So it is like any stage you can take. Okay. So that is why you should read about the training history of that models. Okay. So what I'm trying to say here is when you want to do this fine tuning, right? So this is the pre-trained model. Either you do SFT or you do a task specific train. And SFT is not mandatory. Okay. So after pre-training, you can do fine tuning also directly. Okay. This you can completely skip also because the SFT is for what is called for instruction following. So if your model, you don't want your model to follow instructions, you wanted it to just give an positive or negative. For example, any given sentence, your model is supposed to give either it is a positive sentence or negative sentence. That it is not a following, it is also following instruction only, but you can do that fine tuning. So fine tuning is also like structured SFT, right? So it is ideally both are same only. Okay, we call this SFT because Chat GPT did that first time, first. So first time when they released a chatbot, they released this at this point. So we normally consider this as part of providers work. So ideally, this is also one SFT, sorry, fine tuning, structured fine tuning. Okay. So this fine tuning also you can do. That is why I will say this is not mandatory step. SFT is not a mandatory. You may get this SLM. You can fine tune it directly to your whatever is telling you. So here, if you say you take the pre-trained model, you can fine tune it and then get this. But point is, if you do a fine tuning, complete model, it will be like too much of memory. You understand, right? 4 bytes. So 4 bytes storage memory itself is 28 GB. Correct. When you are doing fine tuning, I guess it is 4 times. So I think in the earlier time, I made a mistake. Just if you are with me, just understand. If I say, I will tell you one simple thing. It will correct my earlier mistake also. So if I say LLM or SLM is having 10 GB, sorry, 10 billion parameter, no, not 10 billion, 4 billion parameters. This is the parameters. Okay. So now you convert this into storage memory. For storage memory, the original model, you will multiply by 4. Okay. Because this is 4 bytes. That's what we saw. FP32 training means it is 32 bits. So FP32 training is done for the original model. So every every parameter is 32 bits, which is 4 bytes, correct? So if you take this 4 billion model, it will be 16 GB of storage memory. This is only for storage. Okay. If you want to do inferencing on this, okay, inferencing on this 16 GB. So now you have stored this. Okay, if you want to do inferencing of this, consider 2 to 2.5 times. 2 to 2.5 times x. Okay. So I think earlier what I made was mistake was I multiply 4 billion into 2.5, but consider that you have to multiply that with this. Okay. So 16 GB into 2.5 is around 32 plus 8 is 40. So 2.5 manlo. So it is 40 GB of inferencing memory. Okay. Okay. Now another one is fine tuning memory. So inferencing is just you are giving an input, it is giving an output. Okay. So you need 40 GB. Okay. So it has to, it's not exactly 40 GB. Worst case, I'm telling, 2 also sometimes chalega. Okay. It depends on layer normalization, where it is placed, how many heads are there, so many factors. So consider 40 GB is the worst case. Okay. So now fine tuning memory. So during fine tuning, how much memory is it? So consider approximately 4x. Okay. 4x. This is for your business use case. I'm telling. Nothing is exam related. Exam related also same logic only you can write. You'll be fine. Okay. 4x times. It is like 64 GB RAM you should have. Training memory means these two are RAM. Okay. So RAM or okay. So RAM requirement in inferencing. When you do inferencing on the model, 40 GB. When you do inferencing on this model, it is 64 GB. Okay. So now this much RAM is not available, right? So what do you say? It's a 4 billion parameter. Why I have to do all these things? So that is why you have a quantization. But lot of people would have pulled 4 billion model and run it because you pull the quantized model of it. You will not pull that FP32 model. Okay, that's the point there. Okay, FP32 is the original model, but you would have quantized it. So quantized it means if you take it as half also, it's very less, right? You take N4, N4 is 8 times lesser. So all these things you just reduce by 8 times. The storage is 4 GB. Okay, storage and inferencing is 10 GB. RAM, this is RAM, this is hard drive. Okay, and this 64 divided by 4 is 16 GB for training. Okay, this is also RAM. Okay, so you will require this much RAM to proceed with your training. Okay, so that is what we are talking about. So 7 billion parameter for storage is 28 GB. So if you do a fine tuning, approximately 4 times space RAM chahiye. Okay, so it is like 56, 112 you require. But if you do, nobody does this full tuning, full fine tuning. Okay. So you find everywhere POCs, LoRa will be done. LoRa is you don't touch the main one. Okay. Main matrix you don't touch. So it's like this is your main matrix. Okay. You don't touch this at all. You only tune this additional one. What is this additional one is this one. So this B into A. B into A, what it is it is similar to W. Okay, it is same as W. Like for example, W is 3 cross, not 4 cross 4. Okay, so for example, इतना छोटा तो नहीं होता है. So 4 cross 4. Okay, so this is W. But if you want to this delta W, what you mean is I wanted to change each of these 16 values. 4 cross 4 means 16 values by minimum amount, right? So that is what is the requirement of fine tuning. Fine tuning, as I said, it is not going to move mountains. It is just that you are trying to take one tree from here and then put it somewhere else. One plant from here and put it somewhere. So minor changes of a big mountain. Okay. So that is what you should do, because if you change the complete all the trees in the mountain, then it will not speak English at all, because the basic knowledge, the generalist knowledge is the core. You cannot make that, you cannot wipe it out. If you change so much, then everything it will forget, right? So fine tuning can only, that is why it is specifically called as fine tuning. It is not complete training. Okay, it is just fine tuning. So this delta W is also 4 cross 4. But point is, you don't use this. You say this as a B cross A. B cross A means you will put 4 into 1 as B and A is 1 into A. So sorry, 1 into 4. So if you know matrix multiplication, you understand that 4 cross 1 multiplied by 1 cross 4 matrix is 4 cross 4 matrix. Okay, so instead of fine tuning 4 into 4, 16 parameters, now you are going to fine tune only. This is 4 into 1 is 4 parameters and 1 into 4 is 4 parameters. 1 into 4 is 4. So you are going to only fine tune 8 parameters instead of 16 parameters, right? So that is the logic behind this. So you are going to fine tune only these 8 numbers. So 8 numbers is, so you can now if you indirectly want to calculate, so 8 numbers is 8 into 4 bytes, right? So 32 bytes. 32 bytes. For training, it would have been like 4 times of this 32, which is 128 bytes. So this much is only required. But originally, if you see, this W had 16 numbers, right? So 16 numbers means it would have been 256 bytes. This is a very small number I'm talking about, but if you take 7 billion parameters, it will be like so much. Difference will be so much. So that is why we are doing a LoRa fine tuning. LoRa fine tuning is we are, instead of this main W, we are creating a matrix of same 4 cross 4 size. But how are we creating this matrix is multiplying two smaller matrix and creating. These numbers are created from this multiplication. Okay. And only these numbers are getting tuned during your fine tuning. Got it? Oops, 10 minutes extra. Okay. Understood. We'll continue from here. Any questions on this? I'll stop the recording. Anybody wants any answer, any questions?